Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to start our unit that involves double and triple integrals. And really, honestly, after this chapter, you'd be able to solve really any higher order integral problem. It's just that the algebra involved in solving like a 4 integral or a 5 integral or a 6 integral problem is just so much that basically once you learn how to set up an integral for like 2, 3 integrals, you typically just let a computer take over, basically, for the higher ones. But what you'll notice here is a lot of this stuff is basically just being built off of what you know from integrals in Calc 1. And this is one of those times where if you really understand what an integral is in Calc 1, you're going to totally understand what a double integral, like this one down here is. And so I want to start with kind of taking your thinking from area last year and switching over to volume. So as we go up in dimension in math, we change kind of the physical problem a lot of times, right? So last year we were finding the area under like a curve, right? We might be finding this shaded area here. And now what we're going to basically do is we're going to find the volume under a surface, right? So no longer am I going to call it a curve because that's like a 2D thing. But in BC Calc, you get area under a curve. In Calc 3, you get volume under a surface. And the way we did this basically with area last year is the way you want to look at this is honestly area equals length times width. What we did was we have, maybe I'll do it like this. So you've got length is that f of x sub I star, and then you've got width, and that's the delta x. And I guess it could really be switched, but one of those is one of those, the other one's the other one. And basically what it is right, this is the idea of the Riemann sum that you learn about. And delta x is literally just a change in x down here, right? And it's, what we're basically going to do is we're going to take a limit eventually and have infinitely many rectangles. And so this delta x is what's going to actually shrink. Delta x is going to go to 0. We're going to have like super small little rectangle. But right now, that's delta x right there for each of these. And then f of x sub I star is basically the height, right? The function value. And you can do things like a left Riemann sum or a midpoint Riemann sum or a right Riemann sum or something like that. And those were ones where, you got the rectangle to match perfectly on the left side every time. What we're doing here is we're basically just saying when we write x sub I star, this is our way to talk about some sort of arbitrary x in, the delta x, basically. So we're picking just like, basically just literally blindfold yourself and throw a dart somewhere over here, and whatever x you pick in there, you evaluate the curve at that spot. That's why you see different dotted lines here. And then you do like basically length times width, and that's your rectangle that approximates that area part. And you just keep doing that and keep doing that and keep doing that. And if you take the limit as the interval, the number basically of those intervals gets smaller and smaller, or gets higher and higher and higher, right? Then you're going to get a better and better approximation, right? Because if you had really small intervals, right, they are going to better fit that curve as you go. And you're not going to get, things like this chunk up here, which is throwing off your data a lot. That little piece up there, is too much area for that first rectangle. And also, I guess, down here, right, there's a gap. We're counting some area down here. So that is basically an integral in, one-dimensional integral from last year. And a double integral is just the same idea, but it's gonna give you volume. And basically what you're going to do is you're just going to do this kind of summation twice. And I have another slide where I'm going to kind of go over it some more. But basically, really simple. Instead of getting, just a bunch of rectangles going across left and right, you're going to get rectangles that go left and right, but also kind of forwards and backwards. And so you're going to get these kind of three-dimensional rectangular prisms, and you're going to sum over all those. And as you shrink the sizes of these things, you're going to get better approximation of the volume. But this is kind of the more specific breakdown here. So this is really what we're doing. So when we do a double integral, it's two summations, okay? You basically are going to have a summation every time you have an integral in math. So they go hand in hand. So when we do triple integrals, you're going to have a triple sum, basically. And you're always going to limit the amount of this, you're going to make those little rectangular things smaller and smaller and smaller. And by doing that, you'll get better and better and better approximations. And so, if we have some sort of region R, this is the actual proper notation that we use. This kind of notation, A comma B cross, that's actually how we read that. We read this as cross. It is not multiplication. But A comma B cross C comma D, those intervals, the first one is the X stuff, and the second one is the Y stuff, okay? And basically what what we're going to do is we're going to take the region R, and we kind of grid it out with AB in the X, and then CD in the Y. And then, what this is doing is we're saying that we're splitting AB into M subintervals and CD into N subintervals, right? And as you do bigger M's and N's, right, you would basically get more and more and more of these grids. You get more entries in your spreadsheet, sort of, right? And then, whereas before we took a sample point X sub I star, now we're going to take X sub ij star and Y sub ij star, and J's are just the Y ones and I's are the X ones. So you can see like X sub I minus 1, X sub I, Y sub J minus 1, Y sub J. So that is actually the correct notation for that stuff. And then you just pick a point in there, and then you do the same kind of thing. You're literally just doing length times width times height now. So, before we did area equals length times width, now we do volume equals length times width times height. And that is exactly what we got right here. F of X sub I, Y sub J is like we can think of the length. And then delta A is, this thing is basically dx dy now. And so you can think like, okay, so this is F of X sub I, Y sub J, let's say. You can think W is delta X. And then you can think, I just need another color, we'll go with this one. H is like delta Y, let's say. But this is the change in area now instead of the change in just X. So you can see that this has also bumped up a dimension. So this is the thing that gets super small, just as before this got super small. And when you do that, right, you get super small little square down there. And then if you multiply the area of that by the height of that rectangular prism, you will shrink the sizes of these and get better and better approximation of the volume. So that is all it is. It's a really, logical step up from what we did with area. We're just doing the same kind of thing, but a dimension up. So let's find some of these. So the first ones I want to do are just iterated integrals over bounded rectangles. So right now I just want to do nice rectangular regions, okay? We will do them over weirder regions, and there's going to be some tricks I'll teach you kind of to deal with some of those. But, intuitively, I hope it's not too hard to see that the order of integration doesn't really matter. No, it does not matter. Basically, the idea is if you integrate, like dx, dy, you basically are just doing all the x stuff first, okay? And then, so actually, this one over here would be my dx, dy. So this right here, right, is, like you can think of it as that integral, as like an area integral. And then the dy is just going to take it and move it in the y direction and then give you this whole box. Or you can do the area here and do the area in the y direction first, and then scale it kind of forwards and backwards out of the page almost, and that in the x direction, right? And that will give you then the full volume in this box. So it does not matter if f is continuous on the rectangle. Basically, then you'll have some region R, and you can do this integral as a to b, c to d, dy, dx, or you can do an a to b, c to d, dx, dy. So notice these two are switching, right? Y is always c to d. Y is always c to d. But it's kind of like, we had a theorem like that for partial derivatives as well. And there's one like that for integrals, and it's called Fubini's theorem. All right. So really simple to start off. If you do an integral like this first one, integral of x dy, it truly, the way you want to think of this is, the way I look at it, I guess I'm going to say that, is like if I did the integral of 2 dy, these two are very similar to me. X is a constant with respect to y, right? Just like when we did that with partial derivative stuff, right? If you think of this picture here, x is always fixed on that line, and that's constant for this direction. So there's no reason that you should think of x here as different than like a constant like 2. It is constant in y. So if you run into an integral of like say x with respect to y, and then the way you would do that is you treat x as constant and you would just tack on a y, right? And then you do plus c, right? Because there's some constant integration there. Likewise here, if you're doing an integral of y with respect to x, that is constant, and so you would literally actually just get the exact same thing. You get xy plus c. Y is like a 4 or some other constant number with respect to x. So this is important to remember. You're going to have to do that all the time, okay? All right. So let's finally get into one of, actually we're going to do a few of these integrals right now. So integrals too are really what you're going to see down the road if you go into math and science. Derivatives are important, but it just, the way that the world works, you're going to see that you run into a lot more integrals. And I could talk for a long time about why that is. But you really want to learn these well, because this is honestly what you see most of the time. And we can talk in class sometime about why integrals pop up more than derivatives, but they really are the big ones that you want to know. So just starting off here, I want to find this double integral over a region R that's defined by this. And a lot of times in these problems, what I would do first is I would just draw the region. So x is going from 0 to 2. So 1, 2. And then y goes 1 to 2. So 1, 2. And so basically, you have that sort of rectangular region. And, 0. There we go. You have that sort of rectangular region. So that's what we're integrating over. This right here is my dA, okay? And it does not matter the order we do this thing. So I'm just going to do dx dy. So I'm going to set my integral up. And so I have xy minus 3xy squared dx dy. And then we don't write the parentheses, but you do want to kind of see it this way. Like that's one, that inner integral is the dx one. And so the dx one goes 0 to 2. And then the other one goes 1 to 2. So we got 1, 2, 0, 2. And then you literally just do two integral problems. So you're going to do the integral of that, this first thing with respect to x. And so I'm just literally going to copy down the 1, 2 part. And then integral of xy with respect to x. You can literally just do, x raised up to a power. And then you can just copy the y over because it's constant. And then you'll have minus 3x squared over 2y squared. And you're going to evaluate that from 0 to 2. And then you're going to have a dy. And then you should just go and evaluate. You're plugging in for x, not for y. But go plug everything in for x. And you would get this. Okay. And, it's pretty nice because when you plug in 0, it just kills those terms. So you're literally just doing like 2 squared, 4 divided by 2 is 2, y, and then, plugging in 2 here. And then you just, there's a really nice single variable integral that you should be comfy with from last year. So I'm just going to copy down. You get this. And then if you evaluate, I guess we can, simplify this a little bit here. So we would really get y squared minus 2y cubed, and we're going to value that from 1 to 2. So basically it's like 4 minus 16 minus 1 minus 2, which is negative 11. And that's it. So it's really just doing two integrals back to back, like kind of nested, I guess, is really how you should look at it. All right. So sometimes the order of integration, because it doesn't matter which way you do it, you can do it either way. You should think about, do I want to do dx first or dy first? And so probably the trickiest thing in these problems is just thinking about like the order to do the problem in, okay? And this is actually like parentheses. So this is y sine of xy. And if you look at this, right, you have a product of functions with y, but you only have one x function, right? So it would be a much easier integral to do with an x versus a y. So this is a problem where you really, really need to look at that and realize dx dy is easier than dy dx, okay? You should get the same thing either way, but no one would want to do dy first and then dx. So you'll do dx, then you'll do dy, okay? So if I set that integral up, remember this is x, this is y. So I'm doing 0, pi 1, 2, y sine xy dx dy, okay? And then, the integral of sine here, the sine xy, basically the way I look at that, if you had the integral of, say, sine 2x dx, and this is how I look at it because when I do a dx integral, right, like I'm going to do here, y is a constant. So y is like my 2. Those are the ones where you just do like minus cos 2x, and then you just divide by the constant. You divide by 2, right? Plus c or whatever. But that's basically what I'm going to do. And all these different things I'm talking about, I'm sort of assuming you're still good with from Calc 1. So if you do have questions about these kind of integrals, you got to ask because they're just going to keep popping up over and over and over again. All right, so this is my, the y here is constant too. So in a sense, you can even like think about pulling this out and put it like in between the integrals. That's fine to do. But I just left it there. This is my integral of sine xy. And so I need to integrate, it was a dx, so I'm integrating from 1 to 2. And then I'll do a dy after all of that. And whenever you do, you should never have like an x left over after you've done a dx integral. You're plugging in the x numbers, and that's why this thing should simplify to just a y expression, basically. Right? So if you plug all that in, you get this. And then both of these integrals, right? So like the way I would just do this, I would split it. I just do this one and then this one. And both of these integrals are nice because, they're honestly just like the sine one we did, except truly you do have constants in here, right? And it's a 1, but it's just the integral of negative cosine. So you basically just do the trick where you divide by the constant. So if you do that, you would get this. And then you can just go and evaluate all of that. And if you just plug in pi and 0, you will get this. And it's, you've got signs of multiples of pi. And so literally all those are 0. And so this thing equals 0. And so don't think that this truly means there's no volume under this thing. Just like with area, it's signed area and signed volume. So this just must mean there's the same amount of stuff above or below the xy plane, in terms of volume, right? So like if you think of, I'm not saying this is what it looks like, but if you take, sort of this square down here, and you imagine a cube above it, right, and the volume in that cube, and then you think of a cube kind of below the plane down here, right? This cube, the yellow and the purple cubes would sort of cancel each other out, and you would get like a volume of 0. So that is, what's happening. I mean, you could also just literally have no volume under there, but I'm sure that's not what's happening. I don't know what that looks like off the top of my head, but I'm sure it has some sort of, wave kind of look to it. And because of that, you must be over this region getting equal parts above and below. All right, just one more problem I want to do. So chapter 15 and 16 are definitely where really knowing what these things look like comes back. So it's hard for me to draw it, basically, and you kind of have to do some of the imagining of what's going on in your head a little bit. But this problem asks you to find the volume of the solid that is bounded by the elliptical paraboloid, given by this, and the planes x equals 2 and y equals 2, and the 3 coordinate planes. Ugh. So you can try and draw it. This thing right here, z equals 16 minus x squared minus 2y squared. I'm not going to get it perfect, but it basically looks, like something like this. Something like that. So it's just kind of going down, forever. And it, it's like a basket that's been flipped upside down is basically how I see it. And that's because of the negatives, right, on the variable terms here. And it's like shifted up 16 and things like that. But, basically what we have happening is you have these two planes, x equals 2, which I'm going to say is like right, oh, it's a horrible parallel lines. So that's x equals 2. And then I've got y equals 2, which I'm going to say is like that one, cutting through y equals 2 over there. And then, to kind of cap it off, you could sort of imagine there's like a box there, and so you have this sort of rectangular shape, right? This like rectangle, and that's what you would get with the XY axes, the coordinate planes in the back. But then you cap it off with the paraboloid, right? And so you've sort of put a dome on top of this skyscraper. That's sort of how I see it. So this scribbly picture here is very hard to see. But what we need to know is that the region it's integrating over for sure. And so in X and Y, you're integrating basically a square from 0 to 2 in both X and Y. And so if you just take, this as your surface and you integrate over that region, right, that would find the volume inside the skyscraper-y thing right here. That's the idea. So I'm going to set that integral up and just do 0 to 2, 0 to 2. I put in my function negative x squared minus 2y squared plus 16. And, this is one where it really doesn't matter if you do x then y or y then x. They're equally easy. If I do dx then y, I would get, for the dx part, I get this. Basically, everything just gets multiplied by an x, right? X squared gets multiplied by x. Negative 2y squared gets multiplied by x, and 16 by x. And you divide by 3 for that one. And then if you go and evaluate, you would be able to simplify this thing down to this. And that's just a nice kind of quick integral in y. You get this. And if you evaluate that from 0 to 2, you get 48. So that is the volume, basically in an object that sort of looks like this. If I draw that picture a little bit better. So roughly like that. You're finding the volume inside of something kind of like that. It's got like an upside down paraboloid on top, and then it's inside of that kind of rectangular prism, and it ends down here in the XY plane. It doesn't go below there because of the coordinate planes part. So that is basically the idea with double integrals over rectangular regions. Basically, you're just, doing one integral like this, and you're just thinking, if I do it a dx one, y is our constant. And so they just acted the same way as like a 16 would. And then you just plug in the numbers, and you do, the dy one following that. And I won't be asking you to do dx, dy indefinite integrals. I'll only ask you for ones where you plug in. And I can talk about why that is, but they're really complicated, and we don't need to get into it right now. So you'll only see ones with numbers here right now. You won't see like dx and then no numbers, and dy no numbers. That's a much harder thing.